Okay, hi again. This is the second part of my talk. And I told you that in this part, I will give you an idea of how to prove this theorem 2, which states that if we have a Maslov zero embedded exact Lagrangian cobordism from lambda minus to lambda plus, then the number of augmentation of lambda minus is less, like up to equivalence, we will see what I mean by this, is less or equal than the number of augmentation of lambda plus up to equivalence to. Let's say that here we are with, we work with Z2 coefficient in order to compute something. And we don't need other extra assumption on the Lagrangian cobordism. So remember that we were using this theorem in the following way. In the previous talk, we found, like, we used it to prove that it's not always possible to reverse the procedure of Lagrangian surgery on Lagrangian cobordism. And to prove this, we found a family of, like, for example, we found, among others, we found a family of Legendrian links, lambda or Legendrian knots, lambda GP, that admits a VAC filling, so which means vanishing index and contractible. So Maslov zero exact Lagrangian filling with double points that have condensator 1 and are simultaneously contractible. So this lambda GP admits VAC filling of genus G with P double points, and we prove that it does not admit the VAC filling of genus G minus 1 with P plus 1 double point in the following way. So it's, if such a filling existed, so for example, this, so in this case, P plus 1 equals 2 and G minus 1 equals 1. So if such a filling would exist, then we have seen, so by some theorem, this is equivalent to the existence of an embedded Maslov zero exact Lagrangian cobordism from, like, P plus 1 copies of the Hopf link to the knot. And then we have used this theorem 2 to prove that such a cobordism cannot exist because the number of augmentation of the positive end here was, like, strictly smaller than the number of augmentation of the negative end here. So that's how we prove that this lambda GP does not admit VAC filling of genus G minus 1 with P plus 1 double point. Okay, so we're going to prove this theorem 2, or give some ideas at least. So remember first that if I have an exact Lagrangian cobordism from lambda minus to lambda plus, it gives rise to a DGA map from the Chekhanov-Eliashberg algebra of lambda plus to the Chekhanov-Eliashberg algebra of lambda minus. And via such a DGA map, we can pull back augmentation of the negative end to augmentation of the positive end. So if epsilon minus is an augmentation of lambda minus, or of A lambda minus, then if we compose it by this DGA map phi sigma, it will give an augmentation of lambda plus, what we call epsilon plus. And what we actually prove is that this map is injective on equivalence classes of augmentation. So this map that takes an augmentation in the negative end and gives an augmentation of the positive end is injective on equivalence classes of augmentation. So if I am working, like, with Z2 coefficient in particular, this theorem 4 implies theorem 2. By injectivity, I get this relation about the, like, the cardinality of the sets of augmentation up to equivalence of the set of equivalence classes of augmentation. Okay, so now maybe what I should tell you is what is this equivalence relation? And this is equivalence relation in the augmentation category. So the augmentation category is an A infinity category. A first version was first was first defined by Bourgeois and Chantraine, but this version does not have any geometric unit. It doesn't have a geometric unit. So we will work. So it will be easier, like, to define an equivalence relation in this category, OG+, which has been developed by Ng, Rutherford, Chen, de Sivek, and Zaslow. And this category admits a strict unit. So it's an A-infinity category, meaning that it has a set of objects, which in this case will be augmentations of my Legendre. Then we have some morphism spaces between two augmentations, which will be denoted home plus. So these morphism spaces between two augmentations are given by the vector space generated by rep chords from lambda 2 to lambda 1. So what are these lambda 2 and lambda 1? Lambda 2 and lambda 1 is forms like a 2 copy of my Legendrian lambda. So if I have my Legendrian lambda here, or like the blue one, I take a 2 copy. So I take a lambda 2, or I take like lambda 2, which is my Legendrian, and I take a push off in the positive red direction, lambda 1, that I call lambda 1. And then this link admits an infinite number of rep chords. Like there is a S1 of rep chords here or around. So I take a Morse function on lambda 1 in order to perturb it and get a finite number of rep chords. So I take a Morse function on S1 on this Legendrian with only one maximum and one minimum. And this Morse critical point, maximum and minimum, will become some small rep chords that are given by those two intersection points in the Lagrangian projection, or by some small chords here in the front projection. So once I have these 2 copy, I can consider the vector space generated by rep chords from the blue to the black, and this will be my home space between epsilon 1 and epsilon 2. So in particular, this home space does not depend on the augmentation epsilon 1 and epsilon 2, which can be a bit weird, but then the A-infinity composition maps will definitely depend on the augmentation. So these are given by maps MD for D greater than 1. So from the home space of, so I need to take like D plus 1 augmentation, and these are maps, MD are maps from these tensor products of home spaces to home plus of epsilon 1, epsilon D plus 1. And they are defined by a count of rigid pseudo-holomorphic disks with boundary on R times the Legendrian in the similar way as the differential in the Legendrian contact homology. So for example, F1, M1 of a chord B. So if I have M1, it's a map from home plus epsilon 1, epsilon 2 to home plus epsilon 1, epsilon 2. And M1 of B will be defined by the count of pseudomorphic disks like this, with boundary on R times lambda 1 and R times lambda 2, with one negative asymptotic to B, possibly some other negative asymptotic to pure rep chords of lambda 2 or pure rep chords of lambda 1, like the number, it can be arbitrary, and the positive rep chord asymptotic to a chord from lambda 2 to lambda 1. Okay, and we do the sum over all possible A and over all possible numbers of pure rep chords. And this gives the map M1. And then in a similar way, M2 will be defined by a count of curves like this, with 2 mixed rep chords, like negative asymptotic, 1 positive mixed rep chord asymptotic, and a certain number of the pure rep chord asymptotic, etc., for a D greater than 2. Okay, so it is possible to prove that these maps defined this way actually satisfy the A-infinity relation, and the first infinity relation is that m1 squared equals 0. So m1 is a differential. So m1 is a differential. So in particular, we can consider the cohomology category associated to the augmentation category, and the third infinity, like the second infinity relation, implies that m2 induces a product on homology, and the third infinity relation implies that this product is associative. So we have an associative product on this cohomology category. And another fact, important one, is that this category is unital. So meaning that for each augmentation epsilon, there is an element E epsilon in this home space. And in particular, so it is given by the sum of the minima. So the sum is because if my original lambda has several connected components, I need to take a Morse, I need to take a Morse function on each component, and each Morse function will have a max and a min. So I have to take the sum of the minima on each component. So it's in particular given like on the Lagrangian projection. If this is Lagrangian projection, this is the min and this is the max. So this minimum is this red curve. Okay, so now that I have a unital category, I can say, I can define what it means for two objects, so two augmentations to be equivalent. And so epsilon 1 and epsilon 2, two augmentations are equivalent if and only if there are co-cycles alpha and beta. So alpha is in like the home space, so the morphism space of epsilon 1, epsilon 2, and beta in the home space of epsilon 2, epsilon 1. They are like degree 0, and they are co-cycles such that M2, so the product of beta and alpha in homology gives the unit epsilon E epsilon 1, so there should be it should be in homology here, and M2 of alpha beta gives the unit of epsilon 2. Okay, so this is the definition of equivalence of augmentation. So now we can prove the theorem stating that this map from epsilon minus to the pullback augmentation epsilon plus is injective on the equivalence classes of augmentation. This result was actually proved by Yu Pan in her thesis, but she did it for the case of knots, not for links. And in order to prove this, she used the functoriality of the augmentation category under cobordism, meaning that there is so if there is a cobordism from lambda minus to lambda plus, there is, it gives rise to a infinity functor from the augmentation category of lambda minus to the augmentation category of lambda plus. But this functor is not well defined for links. So it's not possible to apply this proof for the case of links. That's why we need to do something else. So what do we want to prove? We want to prove the following. We want to show that it's if like epsilon 1 plus is equivalent to epsilon 2 plus, the injectivity means that we want to show that this implies that epsilon 1 minus is equivalent to epsilon 2 minus. So explicitly with the definition, if there are like two cocycles alpha plus and beta plus in home of epsilon 1 plus, epsilon 2 plus, and home of epsilon 2 plus, epsilon 1 plus, if there are cocycles such that like the products of the cocycles give the unit of epsilon 1 plus and epsilon 2 plus respectively, we want to prove that this implies that there are cocycles alpha minus and beta minus such that these relations are satisfied too. So we will need to prove, in order to prove this, we will need a map called iota from the home space of epsilon 1 plus epsilon 2 plus to the home space of epsilon 1 minus epsilon 2 minus. So if we have such a map, which has the following properties: that it preserves the product and it is unital. Then we are done because of this. So if we can construct such a map which preserves the product and is unital, then we just have to use it to push down the cocycles alpha plus and beta plus to get alpha minus and beta minus. So indeed, we take iota, we apply it to alpha plus and beta plus, and we take the product in the augmentation category of lambda minus M2 minus. Then if iota preserve the product, this is equal to iota composed with the product in the augmentation category of lambda plus applied to beta plus, alpha plus. Then we know that epsilon, like epsilon 1 plus and epsilon 2 plus are equivalent. So this is equal to the unit of epsilon 1 plus. And if iota is unital, then this gives the unit of epsilon 1 minus. And then we would get, so we have also the reverse relation with alpha plus and beta plus, and we get exactly that epsilon 1 minus and epsilon 2 minus are equivalent. So the only thing to do is to construct such a map iota. So how do we construct it? We will use Floer theory for Lagrangian cobordism developed by Chantraine, Dimitrov-Glurizel, Guigini, and Golovko. So namely, what did they do? They consider two exact Lagrangian cobordism, which are embedded, and assume that they intersect transversally, and they define a Floer complex associated to this pair of Lagrangian cobordism. So if we have sigma 1 and sigma 2, two exact Lagrangian cobordism embedded, the complex associated to it has three types of generators. The first are rep chords from lambda 2 plus to lambda 1 plus. So rep chords in the positive end from the copy 2 to the copy 1. This is actually the home space of epsilon 1 plus epsilon 2 plus. Okay, we assume that the negative end admit augmentation, like epsilon 1 minus and epsilon 2 minus, that we pull back by the DGA map. Okay, so we get epsilon 1 plus and epsilon 2 plus. And the other types of generators are the intersection points between sigma 1 and sigma 2. And the last types of generators are rep chords from lambda 2 minus to lambda 1 minus. So again, it's exactly the home plus of epsilon 1 minus and epsilon 2 minus. Then the differential is is this kind of matrix. It's a 3 by 3 matrix with 0 here for energy, like for action reason. And so this map D++ is just the M1 map in the augmentation category of the top. And this D minus minus is also the M1 map of the augmentation category of the bottom. Then, for example, this D00 is defined by a count of Floer strips with boundary on lambda 1 and on sigma 1 and sigma 2, etc., etc. Okay, so this is, they have proved that this is a differential. So D square equals 0. And moreover, this complex is acyclic, which implies that this map psi, which is D plus 0 plus D plus minus, is a quasi-isomorphism. So it's a map from this complex that I call CF infinity of sigma 1, sigma 2, generated only by intersection points and rep chords in the negative end, from this complex to the complex generated by chords in the positive end is a quasi-isomorphism. And in our context, we will consider sigma 2 to be a copy of sigma 1. So it's a small perturbed copy of sigma 1 in such a way that this map for action reason will be 0. So the complex will actually look like this. So it looks like this. So if you're used to look at complex like this, you will see that it has actually a structure of a double cone. Okay, so first, if I look at this submatrix, it's an upper triangular matrix. So it's a cone of a map. So the complex CF infinity with this submatrix is the cone of a map D0 minus. So if I take the long exact sequence in homology associated to this cone, I have such an exact sequence. So from the complex, so the homology of the complex generated by intersection points to the homology of CF infinity to the homology of the complex generated by chords in the negative end. And then when I look at this entire matrix, this is the cone of psi. So which means that by acyclicity, again, it means that this middle part is quasi-isomorphic to the homology of the complex generated by chord in the positive end. So which is given by psi minus 1, induced in homology. And then if I call, so this is the projection induced by the cone. And I define the map iota to be equals to pi composed with psi minus 1. Okay, so the last part, so this is how the map is defined. And then in my thesis, I proved that there is a product structure on this complex CF infinity generated by intersection points and chords in the negative end. This map induces well-defined products in homology. And moreover, in homology, the map psi preserves the product. So takes the products on this complex CF minus infinity to the products of the augmentation category in the positive end. In particular, as psi is the quasi-isomorphism and preserve the product, it implies that it is unital in homology. And so what remains to prove, because if you remember, we want to prove that iota preserves the product and is unital. So iota is this composition of map. We have proved that this first map is unital and preserve the product. So what remains to show is that the map pi preserve the product and is unital in homology. So this is a little bit more tricky, like involving some properties of the Cthulhu complex when by concatenation of cobordism and using some properties of transfer maps. So I will just stop here for this proof, but I hope it gives you an idea of how this works. Thank you.